Welcome to the Wright Science Daily Revision Boost. First of all, congratulations to our top 3 scorers on our Day 12 quiz, which were Ravina and Zenden, Aoife and Molly. Well done, let's see if we can keep it up. Today's daily formula is that for the energy transferred. So energy transferred in joules is the charge in coulombs times potential difference in volts. In today's Daily Booster, we're going to have a little look at another type of exam question, which is those ones based around those assessed practical tasks. So there's a range of different questions that we could see associated with those experiments. We could be asked about variables, we could be asked about bits of equipment, the results and how to process them, we could be asked to draw a graph, or how to conclude or evaluate an experiment. If we consider the variables first of all, then we've got 3 types of variable that we need to know. The independent variable is the one that you are changing. So if they were to ask you to identify the independent variable, you read the information it gives you and find out what's changing. Write that down. Dependent variable is the one that you are measuring, and your controlled variables are other things that could change, but we want to keep them the same to ensure it's a fair test. So an example of the kind of question we could be given here is on the left. So as always, when you're given this question, don't skip straight to the bit that says A, because the bit at the top gives you useful information. So get a highlighter and underline or highlight the key bits that are important to you. So that means you don't have to keep rereading it. So the first one we've got then, catalase is an enzyme that is going to break down hydrogen peroxide. So we can have the fact it's an enzyme is important first of all. The amount of oxygen released can be used to measure how fast the catalase is working. The student investigates if the catalase works faster at 30 or 40 degrees Celsius. She counts the number of bubbles of oxygen released in 1 minute. And then we've got a diagram of our apparatus there. And then what we need to know is how the student can keep the flask at a constant temperature. So in this case, what we need to think about is, rather than what variable are we needing to control, they've told us that, it's just how can we keep it at a constant temperature. And the answer to this one is actually a rather simple one. Place the flask in a water bath. If I can spell it right. There you go. So we mentioned one bit of equipment there of a water bath, which is how we can keep things at a constant temperature. And that's obviously a slightly more specialist bit of equipment, but it always scares me just how little we know about the names of basic lab equipment. So a quick reminder of a few bits that you might have to use when writing methods or when suggesting improvements. We have a beaker, a conical flask and a test tube. 3 things that we can put substances in. Obviously think about which one's the most suitable for any given application. Then we come on to the different measuring items. So the one on the far left, it's not a jug or anything weird that you might refer to. It's a measuring cylinder. Make sure you do use the correct term, because if you're writing down measuring jug, you're not getting a mark. So measuring cylinder on the left, thermometer for measuring temperature in the middle, and then a gas syringe for measuring the volume of gas on the right. Then we come on to the 2 types of pipette, so the one that you use for measuring small quantities at the top there, and then the one with the bulb filler for things like your titrations. We've got the burette, which again we use in titrations, that contains the acid, and then we have our delivery tube, which is going to connect one reaction vessel to going under into a trough of water or something along those lines. The next section we're going to consider is the results section. So first thing, we need to know a few key facts here. Whenever we talk about an anomaly or an outlier, that's a result that doesn't fit the expected pattern. So quite often you'll be asked to identify the anomaly. So that's the one that doesn't fit the pattern of the rest. When we have an anomaly in a set of data, we do not use it when we calculate the mean. When we're actually using experiments, we should all do them more than once in order to make sure the results are reliable, and it allows us to identify any anomalies. If you only do it once, you could have an anomalous reading and you wouldn't have a clue. And then finally, you could be asked to calculate the mean, which hopefully we know from our maths lessons. We add together all of the results and then divide it by the number of results. Obviously, if you've had an anomaly in there which you've then removed, do remember to remove 1 from the number of results as well when you're dividing. So to give you an example of the kind of question that we could see here, then this one is about the results. So the student writes down her results for 40 degrees Celsius in her notebook, and we're given those results in this section here. Complete the table to show the results for 40 degrees Celsius. Now this is one of those questions that's actually incredibly easy because we're counting, but people will throw away these marks because there's no big answer line. So when you're quickly skimming through an exam paper and ignoring all that information at the beginning, people miss these ones where there's just gaps in a table. So go careful not to throw away easy marks here. So all we need to do to get this one is we're going to come back and obviously have a look. The first count, we've got 5, 10, 15, which we put into our first section there. Then our second count is 5, 6, 7, goes into here. And then we need to work out the mean there, which is just going to be our 15 plus 7, which gives us 22. Divide that by 2 will give us our mean of 11. So you get 1 mark for working out the 2 counts, so by adding up and writing them in, and then 1 mark for the mean there. So part C of this question then tells us the student takes another reading at both temperatures. This will improve her investigation. Explain why. So this goes back to what we've already said about why we should in science always do an experiment more than once. So this is a 2-mark question. I've cut that bit off because it wouldn't fit on the screen. But for our first mark, we can just say that it allows us to identify any anomalies. And the second one is it makes it more reliable. The next question we're going to look at is on the left here. Ali investigates the effect of light intensity on photosynthesis in plants. The diagram shows her investigation. So do look at the diagrams here because they are important and they do give us information. Ali puts the pond plant 0.1 meters from a bright lamp. She records the time it takes the bubble to move 10 millimeters. And Ali repeats her investigation with the lamp at different distances. So if we now have a little look and see what we've got in terms of the results, then what we can see here is we've got the table of results. Now what we need to look at first of all is which distance has an anomalous result for trial 2. So first thing, come straight to trial 2 and then we're going to have a little look down. So as we can see 0.1 to 0.2, then we've gone from 175 to 178. Then from 0.2 to 0.3 it's gone to 187, then it's gone to 243 and then to 268. So there's nothing obviously out of line just looking down the one column, but when you compare it to trial 1 and trial 3, which are the same experiment, just done obviously 2 other times, then what we can do is have a look through the rows. So we can see there that all of those are pretty close to each other, they're fine. These ones, 182, 178, 177, again, pretty close, nothing to worry about. This one, 211, 187 and 208, 187 is out of sync because we'd expect it to be somewhere around about 210 again, and it's not. So when it comes to our anomalous result, then our answer would be the one for 0.3 meters. Second question then, how should anomalous results be treated when processing data? Think back to what we said about calculating a mean. We do not include an anomalous result when we calculate a mean. So all we need to do there is say ignore it when calculating the mean. And then suggest one way Ali could improve her method. Then we go back to that diagram we had at the beginning. So when we've got a lamp shining onto a small test tube filled with water, hopefully one of the things that we're thinking that could change at this point that we don't want to is the temperature of that water. So what we need to do is find a way to stop the temperature increasing. And one thing that we can do is we can place what's called a heat sink in that position there. So that's one thing we could do, is use a heat sink between our potometer and our lamp. We could also talk about the fact that we can repeat for our trial 2 for 0.3 meters, or we could talk about increasing the range of distances. We've only got 5 there, so we could just talk about the fact that we could do more distances or a greater range of distances. So all you need to do, because it's only 1 mark, it tells us one way in bold letters there, then just pick whichever one you want. So I'm going to go for repeat the trial 2 for 0.3 meters. But any of those would be valid to get you the mark there. So when it comes to suggesting one way to improve the method, you do need to look back at that first bit of information. It's go back to the basics on what are the controlled variables and are they being controlled. So when we're thinking about controlled variables, it's about volumes, masses, times, temperatures and concentrations. So look for those key aspects, which ones are not being controlled, say how to control it. The next area that they will ask you about on at least one of your exams is to draw a graph. Now, this is something that could potentially be worth up to 5 marks for you. So drawing the graph is important. You can't just see that bit of graph paper printed on your exam paper and flip the page and think, oh, it's fine, because it could be 5 marks, and that could be the difference between one grade and another very easily. So a few points to remember here. Number 1, use a pencil. You only have that one piece of graph paper printed on the exam booklet. So if you draw in pen and make a mistake, you are not likely to get top marks, because as soon as you start crossing out, it gets very messy, very hard to work out what's actually your right answer. Don't do it. Get a pencil, get a rubber, use them on any graph question. Next one, always use at least half of the graph paper provided. Do not draw some minuscule little graph in the bottom left corner that takes up 2 squares. Number 1, your actual examiner isn't going to thank you when they come to mark it and they need a magnifying glass to make it big enough to see. And secondly, one of the bits of the mark scheme actually states that you need to have used half the graph paper to get the mark. Pick a suitable scale for your axes based on that, using half the graph paper. Remember, you've got to have each square equals the same amount, otherwise you're throwing away those marks. When we come to plot your axes, your x-axis will be your independent variable, the thing you are changing, and the y-axis, the dependent variable. Make sure you label your axes with headings and units. Just take them straight from the table and copy them into the right places, and then take your time in plotting these points. You get a little bit of leeway. It's half a square, so it can be plus or minus half a square from where it should be. If it's more than that, it's wrong. And remember, one thing that maths teachers like to tell you that science teachers hate them for is lines of best fit do not have to be a straight line. If you're looking at those points and thinking it's a curve, then don't draw a straight line through it. Draw a curve. In science, you can have straight lines, but you can also have curves. So think about where your points are and draw an appropriate line of best fit. When it comes to conclusions, then a conclusion is what you found out from the experiment. Now, this could be one of 2 types of question they ask you. You could be asked to describe what the results show, in which case the way you structure your answer is you say what the pattern is and you back it up with some data. That's it. It's a description. You say what you see. If it's an explain question, so if they say explain what the results show, then we follow the initial part. We say what we see with the pattern first of all, but we then need to say why using scientific information. So that's our scientific knowledge coming in here, hopefully. So it's the pattern, the scientific reason for it, and then back it up with data as well. So remember, describe, say what you see, backed up with data, explain, say what you see, say why it happens using science, and back it up with some data. If they ask you about the evaluating part of an experiment, then this is where we're looking for potential sources of error. So this is the sort of areas you could start thinking about. It's not an exhaustive list, this is just a few quick suggestions. Things like the reaction may not have gone to completion for some reason. If it's something that involves a kind of judgment of when a reaction has ended, or you've got to stop a stopwatch, then human error due to reaction times or judgments come into play. Different sizes, so if we're talking about powders or lumps of things, then they come in different sizes, it could have an impact. Same with bubbles in photosynthesis experiments. Not every bubble is exactly the same volume. We could talk about loss of heat to the surroundings if we're measuring a temperature change, and we could also talk about the fact that something's not completely covered by something else. So if we're thinking osmosis, it might be that part of potato chip wasn't covered by the solution, or if we're doing specific heat capacity, it might be that the heater wasn't completely covered by the substance. So look at the information they give you and think, well, where could things go wrong? And that's your source of error. If they've asked you about the potential sources of error, then they're quite likely to have a second follow-up question, which is asking you how you could improve on this. So this is where we go back to the method and think about what's missing. So have all the variables been controlled? Are they using the right equipment? So if they've already talked to you about sources of error, how are you going to fix those ones that you've suggested? The key ones here to look for are going back to those controlled variables. So look at it. Have they talked about actually measuring specific volumes? If it's just said add some solution, some isn't a scientific measurement. So that means it's going to be inaccurate. So we can talk about use a measuring cylinder to measure the same volume each time. If it's masses, if it says add 2 lumps, lumps are different sizes, so record the mass. Think about how we can control those variables, so times, temperatures, volumes, masses, and concentrations. Obviously not all are relevant to every experiment. Think about which ones are and then say how to control them. Just a quick reminder of today's daily formula, which is energy transferred in joules is the charge in coulombs times the potential difference in volts. There is still a quiz on Socrative for you today, and this time it's just a little formula quiz rounding up all of the formulas we've looked at over the past few days. Hopefully you found today's video useful and that's helped you out with understanding how to answer some of these experiment questions. If there's any other style of exam question or anything you want me to go over that I haven't already done, leave me a comment and I can add that to my list.